Hello, my name is John Shepherd, and I'd like to talk to you about climate change, about what's happening, why, and especially what we can do about it. Now, these days there's a lot of misinformation and fake news around, so if you're listening to a talk like this, it's best to ask, what are the speaker's qualifications for talking about this subject? Very briefly, here are my credentials. I'm a physicist by training. I've worked all of my career in various sorts of environmental science, most recently on climate change, and I think I'm a reasonably reliable source of information. This is an overview of my talk. I'm going to start with some basic climate facts about how the climate system works and about climate change in the past. Go on to talk about projections for climate change in the future, especially beyond the end of the century, and then talk about what we can do with dealing with climate change, how big is the problem, and what are the possible responses we may take. So to start with the facts, the world is getting warmer, and the warming has not stopped. This slide shows the global average temperature from millions of thermometers all over the world, analysed by 3 different groups, and all of whom show the same overall trend with some very small differences between them, and that trend continues to this day. Secondly, we know that carbon dioxide in the atmosphere is increasing. It's been doing so for the last 100 years, but only since the beginning of the Industrial Revolution. Before that, it was very stable indeed. This slide shows 10,000 years of history, and you can see that the carbon dioxide has changed only from 260 parts per million to 280 over 10,000 years, and then in the last century has shot off scale. And we know that burning fossil fuels is the single largest cause of this. We can analyse the radioactive isotope carbon-14 and determine that the extra fossil fuel is very old. Next, we know that carbon dioxide is a radiatively active gas, and by that I mean that it absorbs thermal infrared heat radiation, the sort of radiation that all warm bodies give off, including you and me. And in fact that's how it's measured in the lab, and also at the Mauna Loa Observatory in Hawaii that has the longest record of atmospheric carbon dioxide. This increased absorption of infrared in the atmosphere impedes the loss of heat from the Earth's surface. That means that it traps heat and causes and increases the greenhouse effect. And that's really just like closing down a tap that's draining a bath. You expect the water level to go up, and we expect the Earth to warm up if we prevent it from losing heat to the rest of the universe. Carbon dioxide is not the only greenhouse gas. Some other gases do the same. Water vapour, methane and nitrous oxide are important ones. And all of this affects the energy balance of the planet. And that's illustrated in this slide, which shows you an awful lot of what you actually need to know about climate change. On the left-hand side, you can see incoming shortwave, visible ultraviolet radiation coming from the sun. Most of it passes through the atmosphere and reaches the Earth's surface and is absorbed by the land surface and the oceans there. Some of it is reflected by clouds, some of it is reflected by the Earth's surface, and some of course is absorbed by the atmosphere directly. But most of this incoming radiation serves to warm the planet. As it does so, the planet gives off more thermal radiation, shown on the right hand side here, and the warmer it gets, the more it emits. But a lot of this is absorbed in the atmosphere by greenhouse gases and by clouds, and then re-radiated both upwards and downwards, and only the part that's radiated upwards, of course, is emitted to space. The rest goes round in a closed cycle and is trapped, warming the planet. So that's the basis of the greenhouse effect, and higher levels of radiatively active gases cause and increase the greenhouse effect, and the magnitude of this effect can be calculated. It's 19th century physics, and it was calculated by Swedish physicist Svante Arrhenius in 1896. You can find his paper on the web, and it's a wonderful piece of work from very basic observations and very basic calculations, but his answer was very much the same as what we get if we do the same sums nowadays. I mentioned before that water vapour is a greenhouse gas, and in fact a very important greenhouse gas. It causes about 30 degrees of warming of the planet. And without water vapour in the atmosphere, the Earth would be pretty much frozen. It would be minus 15 degrees instead of plus 15 degrees centigrade. And that is very important. And this effect can be modelled, and we can put all these things together either in very simple models or very complex models like general circulation models, and we can check whether the models do a good job of predicting temperatures. So this is a slide from the Intergovernmental Panel on Climate Change showing a whole bunch of models, the wiggly lines in yellow, and the average of those model forecasts in red, and the actual observations in black. And you can see that once we allow for changes of solar radiation, for volcanic forcing, we can find a very good match on average between the models and the observations. This match is not perfect, but we don't expect to be able to model year-to-year variations in temperature, only over a decade or two on a longer-term average. That's because the weather is chaotic, and so to some extent is the average results of the climate from year to year. You can also see that after each major volcanic eruption, the temperature drops a degree or so and then recovers over the next few years. The last big eruption was Mount Pinatubo, and you can see that here. Now, what about climate in the past? Of course, climate has always changed on various time scales, and we need to understand that. I'm misquoting George Santayana here when I say that those who are ignorant of the past are condemned to misunderstand the future. Understanding past climate is very important indeed. And the climate of the Earth has, on a very long time scale, been remarkably stable. It's actually been fairly stable for almost the entire history of the Earth, 4.5 billion years. It's had liquid water on the surface of the planet for almost all of that time, and that can only happen if the temperature stays within fairly close limits. It's actually been especially stable since the last ice age ended about 20,000 years ago, and in particular for the last 10,000 years, the period we call the Holocene, during which human civilizations and agriculture developed. But it's also sometimes been highly variable. We have had repeated ice ages for the last few million years, and the ends of those ice ages, the terminations, show very rapid changes of temperature. So the evidence from the past suggests that climate change is unlikely to be gradual and steady the way most of the models predict. We should expect some lumps and bumps on the way. And we can see that in this slide. You've probably seen something like this before. This is Earth's temperature and carbon dioxide over the last 400,000 years, taken from ice cores in Antarctica. This slide comes from Richard Alley's wonderful book, The 2 Mile Time Machine, all about the data that we can get from those ice cores. And you can see here the temperature in the Antarctic and the carbon dioxide in the air trapped in bubbles in the ice. And I should point out that this slide time goes backwards, so this is the past and this is coming to the future, because that corresponds to depth in the core, and that's the way paleoclimatologists like to plot their data. So here are repeated ice ages and then warm periods, interglacials recurring recently every 100,000 years or so. And here is the exit from the last ice age and the Holocene period. And here is carbon dioxide in the air going off scale in the last 50 years or so. We don't fully understand the source of all these wiggles. We know roughly what causes the ice ages, although we don't understand the processes in great detail. One of the important factors causing these wiggles is believed to be the circulation of the oceans. The oceans transport a lot of heat around the planet. This slide shows the circulation of warm water in red and cold water in blue. And this was first clearly described by Wally Broca. It's called the thermohaline conveyor circulation, and it transports about 1 petawatt of heat into the northeast Atlantic, and most people don't know what a petawatt is, so I can translate that for you. It's the amount of energy output by about 1 million nuclear power stations. It's a lot of heat. And if this circulation is interrupted, if this flow of heat into the northeast Atlantic and elsewhere is prevented, then that can cause major changes of climate. And we believe that changes of this circulation are intimately connected with the occurrence and cycling of the ice ages. So during the last 1,000 years, we have also seen wiggles in temperature. These are records mainly from tree rings, showing various records, all agreeing roughly, but of course these are proxy estimates, not actual measurements of temperature, and we don't expect them to correspond exactly with what we get from thermometers in the present day. But what we can see is that there have been some changes over the last 1,000 years. The medieval warm period, the cold period, the Little Ice Age, coming into the present day and the recent very sharp rises. What do we learn about the natural variability of climate? Is it a source of comfort that climate has always changed in the past? And the answer to that is no. Just because it's changed a lot naturally does not mean that the present changes are also natural. That's like assuming that because the fire alarm when it went off was a false alarm for the last 5 occasions, that it's a false alarm this time too. It's a logical error. Is it a reason for complacency? No. Climate has changed a lot naturally, but that does not mean that human activities cannot still change it a lot too. And we believe that they have. In fact, the evidence shows that the climate system is very sensitive to very small changes of forcing. The ice ages are primarily driven by tiny changes in the amount of sunlight reaching the Earth. In fact, the seasonal distribution of that sunlight caused by changes of the orbit of the Earth as it goes around the Sun. But these sensitivity is not entirely understood, but we should beware because present climate day models are based on our current understanding, and it's entirely possible that they're not yet sufficiently sensitive to the sorts of forcing that we are applying. And future changes are just as likely to be greater than we think at the moment as less. So we should not assume that we are not in for an interesting time. So to summarize the climate facts, it is now ineffectively certain, beyond reasonable doubt in the way that a court would assess the evidence, that global warming is occurring, that atmospheric carbon dioxide is increasing, that it's due to the combustion of fossil fuels and deforestation, and that carbon dioxide is the actor that causes the increases of carbon dioxide to cause changes of temperature. The rates of warming that we see are quantitatively consistent with the changes of greenhouse gases that we measure, and we have therefore a complete and adequate explanation of man-made climate change, and we do not need and have not yet seen any alternative explanation that works. So is the science of climate change still controversial? Well, yes it is, but not in the way that climate dissenters usually assert. There are real scientific controversies, but they're mainly about quite other issues. They are about the rates at which we should expect ice sheets to melt, about the precise impact of clouds, and in particular the feedback effects associated with clouds, the future of carbon sinks like the soils and the oceans, and a host of other issues that do affect our expectations in the very long term. But the evidence for human influence is very strong indeed, and the work done by the Intergovernmental Panel on Climate Change is the biggest and most rigorous collective review of the scientific evidence that's ever been undertaken. There is, as I said, no need for an alternative theory and no evidence in support of any credible alternative. There is a lot of misunderstanding and misinformation. Some of it is caused by ignorance, some of it unfortunately is deliberate. Interest groups engineer an appearance of controversy where no real controversy exists. And this is fueled by the media, by the false balance of taking a climate scientist and a climate dissenter and treating them on an equal footing. And if you doubt that what I say is true, then I suggest you read Naomi Oreskes' wonderful book, The Merchants of Doubt, which explains how misinformation has been used not only to discredit climate change, but also the effects of smoking on health and a number of other controversial scientific issues. Now, I've mentioned the Intergovernmental Panel on Climate Change. Its last report was in 2013. It's due to report again next year, so we will have some updates on its numbers, but we're not expecting any major change in the conclusions. What it said last time is outlined on this slide, that warming of the climate system is unequivocal, that human influence on the climate system is clear, and that the total temperature change up to that time was about 0.8 degrees. Since then, it's continued to rise, and the latest estimates put the warming at over 1 degree centigrade. And they concluded that it is extremely likely that human influence has been the dominant cause of the observed warming. And finally, they predict that the temperature change by the end of the 21st century is as likely as not to exceed a further 4 degrees centigrade, in addition to the 0.8 degrees that has already happened. So that's almost 5 degrees in total. That's illustrated in this slide here, showing in red the expected change of temperature if we carry on with business as usual, and to date we have been carrying on with business as usual. And in blue it shows what we might expect if we do everything we possibly can to limit emissions of carbon dioxide and to get climate change under control. And as you can see, here we have that 4 degrees plus 0.8 that's already happened, and here in blue we have a much smaller increase, about another degree or so, in addition to 0.8. So we might just possibly be able to limit warming to 2 degrees if we really try hard. Now, what about the role of the oceans in all of this? I've mentioned them in context of transporting heat, but they play a very important role in climate change. They are absorbing most of the heat and moderating climate change. They're a big buffer preventing rapid changes of climate, and in fact only about half of the change to which we're already committed has so far occurred. There is more to come in the pipeline as the Earth tries to recover its energy balance. They also maintain global climate patterns, as I mentioned, and they are absorbing much of the carbon dioxide, about 40% of all the extra so far, and they will eventually absorb 80 to 90% of it. From the point of view of global warming, that's a good thing. From the point of view of ocean acidification, that's not so good. And that, by the way, is due to the chemistry of carbon dioxide itself, not to the warming that it also causes. And finally, as the warm water expands, this is causing sea level to rise. It's only a few millimeters per year at present, but it will be up to tens of meters eventually, if and when the Greenland and West Antarctic ice sheets disintegrate. Each will lead to about 7 meters of sea level rise, and that's a lot. The rate at which this happens is very uncertain, but it could be over a meter within the century, and that's shown in this slide here, where we have again the business as usual scenario in red, showing that rise of about 0.8 meters in addition to the 0.2 meters that has already happened, and in blue the steady rise even if we succeed in controlling emissions. Both of those are very long-term processes. The lines are still going up at the right-hand side, and those changes will continue for many centuries after we've ceased emitting carbon dioxide. And that will cause massive flooding of coastal areas. Many of the major cities of the world are within a few meters of sea level, and more than 1 meter of sea level rise is going to cause major problems for people all around the world. We know that the last time the world was warmer than today, about 100,000 years ago, that Greenland was significantly warmer and there was much less ice in the ice sheet, as illustrated in this modelled projection here, and that sea level was therefore and indeed about 5 meters above its present level. The rate of rise was 1 to 2 meters per century, which is much higher than the present rate, but it means that those sorts of rates of change are entirely feasible. And they will have very serious consequences, especially for man's constructions near sea level. This happens to show housing in Florida, but there you can see the same sort of thing all over the world. And these are investments that are very much at risk in the next 100 years. This shows East Anglia, where I live, after 7 meters of sea level rise, and you can see that Cambridge is likely to become a port with access to the sea if that happens, if and when that happens. And I'm fortunate to live about 9 meters above sea level, so I hope that my home would survive even that, but it would not survive the loss of both Greenland and West Antarctica. Now, most of the projections I've shown end in the year 2100, the end of this century, but we hope that the world is not going to end in 2100. We know that natural processes only remove carbon dioxide very slowly, over many hundreds or thousands of years, so temperatures will continue to rise and will indeed remain high for a very long time, even after we have stopped emitting carbon dioxide and other greenhouse gases. So we should expect climate change to continue for many centuries, and so will sea levels continue to rise. And we need very long-term projections of climate change. And for this we need to use rather simpler models than the big GCMs that are normally used to estimate future climate, and that's the sort of model that I used to work on. This slide shows some results from models like that used by the IPCC in its last assessment. It shows the business as usual emissions of carbon dioxide going up, reaching a peak when fossil fuels begin to run out and eventually ceasing when they've been exhausted, or alternatively beginning to decrease almost immediately as we strive very hard to get emissions under control. The temperature changes associated with those scenarios are shown in this graph here, and you can see that by 2300 we could have as much as 6 or 7 degrees of climate change if we fail to get emissions under control, and we're likely to have 1 or 2 even if we do succeed in getting them under control in the near future. So this is a very long-term problem, and it needs to be dealt with as soon as we possibly can. What can we do about it? If we want to achieve the goals of the Paris Agreement on climate change, now 5 years ago, and those goals were to stabilize temperature at less than 2 degrees and preferably no more than 1.5 degrees above pre-industrial levels, then we need to reduce global carbon dioxide emissions at least to the level of the ocean sink, and that means to less than 20% of their current level by 2050 and to zero well before the end of the century. This is a truly massive challenge. It's a big, hard, long-term problem, and unfortunately that's just the sort that our politicians prefer to avoid. If you're interested in what needs to be done to prevent global warming increasing beyond 1.5 degrees, then there is a special report of the IPCC from a couple of years ago that you can consult. The UK's Climate Change Committee reported last year and said that the UK should and vigorously pursue ambitious targets to reduce greenhouse gases to net zero by 2050, and that delivery must progress with far greater urgency. And they made a number of sensible suggestions about the sorts of things that could be done, including phasing out petrol and diesel cars and decarbonising the electricity and heating supply. But they also said that a net zero greenhouse gas target is not credible unless policy is ramped up significantly. And to do that, we need not just policies, we need mechanisms to make those policies actually happen. And that means ways and means of making things happen. Ways and means of mitigating climate change by reducing carbon dioxide emissions. And we certainly need energy conservation and efficiency and low carbon sources of energy to the maximum extent we can achieve them. We need that to allow decarbonisation of the electricity supply and transport. And renewable sources are excellent for doing this, and they are being exploited more, but still not yet enough. But offshore wind and solar energy of all sorts, marine energy from waves and tides, hopefully, eventually, all of these should be implemented as much and as fast as we possibly can. We have nuclear power stations based on nuclear fission. We almost certainly need to keep those going and build some more to supplement the variable supply that we get from renewable sources. Nuclear fusion, of course, is also being worked on and will probably work eventually. And that would be good for generating electricity and possibly also for generating hydrogen, but it would not be much good for road transport and aviation. And in that context I should mention that hydrogen is a wonderful fuel, but it is only a carrier. You cannot go out and mine hydrogen. You have to make it, and most of it is at present made from natural gas, and the carbon dioxide that is the waste product of that process goes into the atmosphere. So we need to do better than that. We need a primary low carbon energy source with which to generate hydrogen rather than using fossil fuels. And meanwhile, while fossil fuels are still in use, we certainly need carbon capture and storage to capture those emissions and store them away safely rather than emitting them to the atmosphere. But it's important to recognize that there is no one solution to this problem. We need horses for courses. And for some sectors we have very good carbon technologies that we know about. This is the ship on which my grandfather ran away to sea. and we've had low carbon shipping for centuries. We know how to do it. We have not yet made that technology up to date, but we could do so. However, for things like aviation, we do not have low carbon technologies off the shelf, and they are going to be very difficult to create, and hence we will probably need to be removing carbon dioxide from fossil fuel emissions for some time yet. So is there a way forward? I believe there is. We should rapidly develop and implement all of these things: large-scale use of sustainable biofuels for transport, decarbonisation of the electricity supply, and carbon capture and storage. These are things we know how to do. This will all take a long time, and so we should start real soon, and the energy industry could and should take a lead. And so I'm delighted that some of the fossil fuel companies are now beginning to act in a way that they have put off for decades. That's a very welcome development. We should also be actively researching a whole raft of technical solutions, such as better storage of both electricity and heat, so that we can even out the fluctuations in renewable energy supply. And as I mentioned, the low carbon sources of hydrogen by using either solar or nuclear power to generate it. But there's no one way to make this happen. We need education so that people understand what is needed. We need economic incentives to make it worthwhile for people to do these things. And we need regulation to make things happen where they would not otherwise happen. For aviation, for example, is not very sensitive to price and almost certainly needs to be regulated to bring its emissions under control. And if we don't do all these things, if we do not succeed in limiting emissions in this way, we may have to consider techniques to intervene directly and try to change the climate. And that is a rather scary prospect, sometimes known as geoengineering. In principle, it may be possible, either by reflecting some additional sunlight away from the Earth's surface, using aerosols in the atmosphere, or by brightening clouds. Or we may be able to remove some carbon dioxide from the atmosphere, not just prevent it being released, but actually physically remove it from the air, either directly using chemical plants, or by growing trees, or by various other techniques that are under discussion. But one would like to hope that these techniques will not be needed and that we will succeed by getting emissions under control. So, looking forward to the day after tomorrow, is it already too late? I don't think so. I think that 2 degrees or thereabouts of warming is now probably inevitable, but we can still do a lot to avoid much worse warming that will happen unless we get this problem under control. It's well worth avoiding 5 degrees or 6 degrees of warming, even if we don't manage to keep it much below 2. And can the sorts of things that you and I can do help? Yes, I think it's essential. I think unless the developed world puts its own house in order, there is no way we can hope to persuade other countries, particularly China and India, Africa and South America, to do something different, to avoid making the mistakes that we have made. And is there a best solution? No. There is no single magic bullet that is going to solve this problem for us. We need horses for courses, different solutions for different sectors of the economy and human activities. We need to forget arguments about whether nuclear power is better or worse than wind power, because we need all the possible contributions to low carbon energy that we can get, as much and as soon as we can engineer them. Now, young people are usually very well disposed towards dealing with these sorts of problems, and people tend to become less enthusiastic as they get older. This shows a slide prepared by a class that my wife was teaching some years ago after a trip to the zoo when they had got to discussing the carbon emissions of getting there and back, and she challenged them to come up with a low carbon form of transport. And here is their suggestion for a pedal bus. And I thought this was a wonderful joke until recently I saw a slide online of a class of children going to school in Denmark, pedaling along a scooter, not entirely unlike this. So such solutions are not science fiction. We could implement them if we wanted to. And so it's with great pleasure that I see that young people are now taking the lead in promoting the climate change action. Not only Greta Thunberg, but also my grandsons, seen on the right-hand side of this slide, on a climate change march in Cambridge a year or two ago. And major companies are also now acting, not only BP and other fossil fuel companies, as I mentioned, but also Microsoft has announced very ambitious plans, not only to become carbon neutral, but to become carbon negative and actually remove its historical carbon emissions in the future. And I sincerely hope that they succeed in this venture. But what can you actually do? Well, Al Gore came up with a list in the back of his book about Inconvenient Truth. The things he suggested are on this slide in black, and the red bits are my additions to his list, and I've put them roughly in order of what I think is their importance. And so you can see that I'm not very enthusiastic about Al Gore's list. I think there's a lot that we can do in addition to that. And for many people in the developed world, one of the easiest and most effective things we can do is to fly less. And we can also, many of us, switch to green electricity with very little or even negative cost. And those of us who have some financial resources can install solar photovoltaic cells to generate electricity, or a heat pump to cool our houses. We can also scrap the SUV and buy a smaller, lighter and more efficient car, preferably electric or plug-in hybrid, and then drive less. And all of these other things on this list. So there is a lot that we can do. We don't have to rely on governments to act for us, although we do need governments to provide the economic incentives that makes it worthwhile to do many of these things. So this is a long-term problem, but it's upon us fairly soon. Many people alive today are likely still to be alive in 2100, and they will suffer the impacts of what we do now. This again is my grandsons. I very much hope that they will be alive at the end of this century, and I very much hope that I will not have to say that their grandparents failed to do what was necessary to preserve the planet for them to enjoy. We have to act in the interest of future generations. Now, I mentioned at the beginning of this talk that there is a lot of misinformation around, but there is also a lot of very good, reliable information. And I would particularly recommend the Real Climate website. Its URL is on this slide, and also wonderful book by glaciologist Richard Alley called Earth, the Operator's Manual. And there is also a video of that produced by the US Public Broadcasting System. The Royal Society in the UK and the National Academy of Sciences in the United States have also tried to produce reliable information. This is a recent report to which I contributed that provides answers to questions, 20 questions in fairly accessible language, and summarizes the current scientific understanding. You can download this free as a PDF file from either the Royal Society or the Academy of Sciences websites. So, in conclusion, Albert Schweitzer was very pessimistic. He said, man has lost the capacity to foresee and to forestall, and that he will end by destroying the earth. Well, I'm not so sure about all of that. I don't think we have lost the capacity to foresee. That's what the IPCC has been doing for many years now. It's what I've been doing, I hope, to help you to do in this talk, to foresee the consequences of our present actions. However, whether we still have the will and the capability to forestall those consequences, I am not quite so sure. However, there is no doubt that climate change is real, that it's mostly caused by human activity, and that it will cause very serious problems, especially for the most vulnerable people on the planet. So the question is, can we fix it? And the answer to that, I'm afraid, is only maybe, but we will have to try very much harder than we have so far. Thank you very much.